like I said, particles do not all move at the same speed at a given temperature. Okay, this equation right here, this is called the Maxwell speed distribution, tells you the fraction, how the molecular speeds are distributed at a given temperature. You'll notice this F is a function of speed, okay, and this is mass over 2 pi, Boltzmann's constant, there's temperature right here, right? And so if you plot that versus speed, okay, F versus speed, this is the graph that you look at, that you see, okay. Now, where this function is at a maximum, the peak in this function occurs at the temperature, at uh, the speed where this function is at a maximum is what you would call your most probable speed. And your most probable speed you can show from this equation using calculus would be equal to square root of 2 RT over m. So the most probable speed you'll see is related to the average speed, which was square root of 8 RT over pi times the molar mass. Okay, and from this you can also get, using calculus, you can get the expression for this average speed. Okay, so this is the distribution of the speeds. The way you would interpret this graph is if you calculate the total area under this graph, okay, the total area is 1. So for any, let me see, I think I got the next line on that one. Okay. The total area under the curve is 1. So if you want to know, for example, what fraction of the molecules have speeds between V1 and V2. So let's say this is V1, 500, and V2 is 1,000, okay, meters per second. If I want to know what fraction of molecules have speeds between V1 and V2, I figure out this area right here. So that would be the fraction of the molecules that would have that much speed between V1, 500, and 1,000 meters per second. The total area under this curve is 1, okay? So this particular curve is for oxygen at room temperature. Okay, so this is for oxygen at 298 Kelvin. This is the function. So that's called the speed distribution function. Okay, before we go to the next line, let me show you an animation that illustrates this. Here's a website, www.chm.davidson.edu/VCE/kinetic molecular theory/Maxwell.html. Okay, here's an animation that shows uh, uh, the molecules at 100 Kelvin. So if you give it enough time, you get here the distribution of the speeds. You'll notice this bar. This is a bar graph. It tells you how many molecules have a particular speed in this particular sample. Okay. Now, what would happen if you were to raise the temperature to, let's say, 500 K? You know that they're going to speed up, right? The average speed is going to increase. And you'll notice, okay, at 500 Kelvin, give it time to settle down. And you'll notice you got more molecules. See, this is higher speed over on this side. Okay, you get more molecules that are able to achieve higher speeds at higher temperature. Okay, so the temperature of your gas is indicative of the average speed. But so the higher the temperature, the speed, higher the average speed increases. That simply means that you have more molecules that are able to achieve higher kinetic energies, higher speeds. So let's take a look at this question right here. The molecular distributions for the same gas sample at two different temperatures, T1 and T2, is shown in this figure below. Okay, so this is T1, this is the blue curve right here is the distribution at T1, and the red curve is the distribution at T2. Which distribution corresponds to a higher temperature? Well, at T1, you get more molecules able to reach higher speeds, right? So T1 corresponds to a higher temperature. How about this one? This is speed distribution for helium and oxygen at the same temperature. Which one do you think represents helium, A or B? What did we say? Remember temperature, okay? they have the same temperature, right? That means you're looking at the same average translational kinetic energy. If you have the same average translational kinetic energy, same temperature, okay, which one will be moving faster? What's the formula for kinetic energy? 1/2 mv squared, right? So, what's the difference between helium and oxygen? If you're looking at the same kinetic energy, let's just compare the average helium molecule and the average oxygen molecule. If you have the same kinetic energy, the higher the mass, the slower the speed would have to be. Okay? So in other words, for an atom of helium and and a molecule of oxygen, if they have the same translational kinetic energy, the heavier one will be moving more slowly. So oxygen molecules would move more slowly at the same temperature on average compared to helium atoms. So that means this curve right here, A, these are slower moving particles, right? So this would be the heavier atoms, heavier molecules, heavier particles. So this will be your O2, and B would represent your helium. Okay. So this would be the faster moving. They have the same average translational kinetic energy, but their speeds, the average speeds, are not the same. The heavier particles would be moving at slower speeds for the same amount of